Welcome to the Explainer. So today we're going to uncover this really powerful AI technique, one that lets models get absolutely incredible results with a surprisingly small amount of data. Yeah, you could call it a shortcut, but honestly, it's a pretty genius one.
All right, so let's just dive right into the deep end. Imagine you're trying to teach an AI how to see, from scratch. Well, you're immediately up against this monumental challenge. You need a massive, and I mean colossal library of labeled pictures just to get it to understand the basics of what it's even looking at.
And, this is the core problem for so many real-world projects. I mean, think about it. Maybe you're a startup trying to build an app that spots plant diseases, or you're a researcher looking at medical scans. You almost never have millions of photos just lying around. So, what are you supposed to do? Well, this number right here, this is a big part of the answer. 1.2 million. That's how many images are in the famous ImageNet dataset. It's this absolutely massive library that was used to train some of the most powerful AI vision models out there, including one called ResNet 50, which we're going to be looking at today. And it's really important to get what's happening during this massive training process. The AI isn't just, memorizing millions of pictures of cats and dogs. No, it's learning the fundamental building blocks of vision itself. It's figuring out what an edge looks like, how to tell different textures apart, how shapes create patterns. Now, this kind of training is super resource intensive for sure, but the result is an AI that has a general, almost universal understanding of the visual world. Okay, so here's the thought. What if you could just borrow all of that hard-earned knowledge? What if you could take an AI that's already like a PhD in general vision and just, give it a quick crash course in your specific little niche? Well, that is the genius idea behind something called transfer learning. And really, when you break it down, it's super intuitive. Think of it like this: learning to ride a motorcycle. You don't start from absolute zero, do you? Of course not. You transfer everything you already know about balance, steering, and braking from riding a bicycle. You're just reusing that core skill set for a new but related task. That's all this is. So let's actually walk through how this works step by step. First, you start with one of those expert models, like that ResNet 50 we mentioned. Then you freeze most of it. You're basically locking in all its general knowledge about edges, textures, all that good stuff. Next, you just tack on a brand new small piece at the very end. This is the only part that's going to learn your specific new task. And finally, you just train that one tiny new part. It's like we're taking this genius expert and just teaching it one small new thing. All right, enough theory. Let's make this way more concrete and actually see how it works in practice. And for that, we've got a great example: teaching an AI to identify different species of flowers. Okay, so here's the setup for our challenge. The AI's job, it has to learn how to correctly identify 102 different species of flowers. But here's the real kicker, the challenge. It only has about 1,000 images to learn from. That's, like 10 pictures for each type of flower? That's it. And then, to prove it's actually learned something, it's going to be tested on a completely separate set of over 6,000 images it has never, ever seen before. Yeah, this is a seriously tough test. Okay, so even when we're using this amazing shortcut, we still have a choice to make. Turns out there are two main strategies we can use to get our expert model up to speed on its new skill. So on one side, you've got the freeze strategy. This is the fast and simple way. You lock down the entire original model and only train that tiny new part you added. You're updating like 0.1% of the whole thing. It's super fast. Then on the other side, you have the fine-tune strategy. With this one, you still train the new piece, but you also unfreeze some of the top layers of the original model. This lets it kind of tweak its more advanced knowledge, things like how petals are arranged, to be a better fit for this flower task. It's going to be a bit slower, but the idea is it might give you a more accurate result. All right, so we've got our challenge, we've got our two different strategies. Now it is time for the moment of truth. Did this so-called genius shortcut actually pay off? Let's see how they did on the flower challenge.
And the results are in, and wow, they are nothing short of impressive. Check this out. The super fast freeze method clocked in at an amazing 87.2% accuracy. That's incredible. But the slightly slower fine-tuned strategy, the one that let the model adapt just a little bit, it actually pulled ahead with a stunning 91.5% accuracy.
But wait, here's where the true power of this technique just slaps you in the face. Look at what happens when you compare our fine-tuned result to what you'd get if you tried to train a model from scratch with just that small flower dataset. You'd be lucky to even hit 70% accuracy. By standing on the shoulders of that pre-trained giant, we jumped up over 20 percentage points in performance. That is a massive difference. I mean, just let that sink in for a second. We're talking about just over 1,000 training images, leading to over 91% accuracy on a test with 102 different categories. That is just a phenomenal, absolutely incredible return on your data. So here's why all this really matters. This isn't just some fun academic exercise with pretty flowers. Not at all. This exact same technique is powerful enough for serious industrial-grade applications. You could take this very same model, swap out the flower pictures for, say, photos of telecom equipment, and get over 90% accuracy classifying that hardware. It's ready for the real world.
And that's really the ultimate takeaway. What this technique does is it basically democratizes access to high-performance AI. You have these massive foundational models built by huge labs, and now pretty much anyone can take them, adapt them for their own specialized tasks, and get state-of-the-art results, all without needing a state-of-the-art budget. It's a game changer.
You know, when you see results like this, it just opens up a whole universe of possibilities. I mean, think about it. Accurately identifying rare diseases from just a handful of medical scans, or spotting a tiny defect on a super-fast manufacturing line in real time. The ability to transfer knowledge this effectively completely changes the game. And it really makes you wonder, if an AI can master 102 flowers this easily, what's it going to learn to